Hi, my name is Jericho Dizon,
And I'm Victor Chiquism.
and our project was about the aerodynamics of a Cessna 182 airplane.
So our project focused on the aerodynamics of a small aircraft, the Cessna 128, the 82. The main goal is to calculate the aerodynamic forces, which is the weight, lift, drag, and thrust during a steady cruising altitude and speed. We approach this in two ways. First is a theoretical analysis using standard aerodynamic equations with published aircraft data. And secondly, we'll be reviewing an existing CFD simulation research paper on the same aircraft. And by comparing the results of the two methods, we can aim to evaluate the aircraft performance and better understand how different modeling approaches can be analyzed.
Aircraft safety and efficiency are directly tied to aerodynamic performance. As in 2023, the National Safety Council noted that over 1,100 accidents occurred in relation to general aviation. This highlights the importance of understanding fundamental flight forces. In this project, our goal is to analyze the aerodynamics of a Cessna 182 airplane and understand how weight, lift, drag, and thrust relate to each other and how they balance each other out. To calculate these forces, we use theoretical models, standard aerodynamic equations, and documented computational fluid dynamic simulation data, and compared results to evaluate performance and to validate our methods. In the case for our airplane, we set some boundary conditions such as no slip, no penetration, and external flow. The external flow accounts for the altitude at which the air density changes. And for our assumptions, we said that it was a steady level flight at constant speed and altitude in order for the lift, drag, weight, and thrust to counteract each other. And moreover, for our other assumptions, we said it was a clean aircraft configuration, so there was no flaps and the gear was up to decrease the level of drag acting on it. Moreover, we said it was a standard atmospheric condition at cruising altitudes. Moreover, the importance of understanding the aerodynamics of a Cessna 182 airplane and airplanes in general is critical in terms of aircraft safety and efficiency, as mentioned in the problem statement of which the National Safety Council mentioned of those 1,150 airplane crashes or accidents, 191 were considered fatal, which were reported number of 304 deaths. Given that the drag and lift forces are the forces that oppose the thrust and weight of the airplane, that keeps it at a constant speed and a constant altitude. By utilizing Newton's law, we realize how the speeds will affect the drag and lift forces in terms of their coefficients. In terms of deceleration and acceleration of the airplane, it is directly affected. It directly has an effect on the drag and lift forces as it is being manipulated by the change of altitude, speed, and angle of attack. Unexpected drag and lift forces during takeoffs and landings are some of the causes for these airplane crashes. In this case, here are the defined input parameters of our airplane, and which we got from Textron Aviation, and which we were able to find the basic dimensions of our airplane, the speeds of our airplanes, and which also in this table we defined the altitude at 10,000 feet or 3,448 meters, and the air density at the altitude was 0.905 kilograms over meter cube. And of course, the gravitational acceleration, which is 9.81.
To calculate our lift force, we are assuming that the plane is flying at a constant speed, which means the forces on the plane will be at equilibrium. So we can set up that lift is equal to the weight of the plane. And by that, we can manipulate the equation to calculate the lift coefficient, from there getting lift force. As you see below, we got a lift coefficient of 0.2178. And using that, we got a lift force of 8,897 0.67 newtons.
And for our drag force calculations, as we didn't know the drag coefficient, we would use the aircraft parabolic drag polar equation, which was acquired from Aerospace Web, which involves the minimum drag coefficient and also components of the lift coefficient, and also the wing aspect ratio and Oswald's efficiency factor, which the table on the bottom right provides for a Cessna 172/178 172 airplane. With that, we've calculated our drag coefficient to be 0.029, and with that, our drag force was equivalent to 1,186.34 newtons.
Well, the stall speed is simply defined as the minimum speed required for the wing to generate enough lift to maintain a constant altitude. Previously, we calculated for the drag and lift forces for the airplane maximum cruising speed. And as below, you can see the different coefficients and forces at the stall speed. And as we assume this airplane flight at a constant speed and altitude, all the forces are all equivalent to the previous force calculated before. However, the significant difference between them are the values of the coefficients. For the simulation, we reviewed an resisting CFD research paper by Highly Innovations. They showed how they used the CFD simulator with the Cessna 182, and as and they use at a constant speed of 100 meters per second, and they showed that they got a coefficient of lift coefficient of 0.954, a drag coefficient of 0.731, and a lift force of 64,540 newtons, and a drag force of 8,422 newtons. Highlighting how the flight assumption directly affect aerodynamic coefficients and calculation forces.
When it comes to our errors, we had a couple of them. For geometry, the theoretical analysis was simplified. The shape or like the shape of our airplane, we assumed it was considered in the drag coefficient that we acquired. And for the computational fluid dynamics simulations that we found, the data, it included full 3D details. And for our assumptions, we only assumed one angle of attack, but however, there's also different angles of attacks or flow conditions. And of course, there's differences in 2D theory and 3D theory. Moreover, we neglected small surface features as we assumed it was already part of our drag coefficient.
For, for our theoretical model, we use the standard equations for lift, drag, weight, and thrust to analyze the airplane in steady level flight. For these for the calculation, we confirmed that all four forces balance each other, meaning the aircraft maintain a constant speed at a constant altitude. Um, when we look at the source of error, we noted that the model doesn't capture the several real world factors like 3D floor effect, surface roughness on the wings, and other more. They are all influence that could cause our simulation results to differ from the actual performance. Even when even those the simplifications, the theoretical ports is still extremely variable, which give us a strong foundation understanding the forces at equilibrium needed for steady flight and serve as a reliable starting point for early design and performance estimation. Oof. and speeds at constant altitudes, observing the theoretical results, our drag and lift coefficient, we can see that as the airplane speed decreased, the value of the drag and lift coefficient increased to account for the slow speed. In order for the lift force to be able to oppose the weight of the plane, usually in these cases the angle of attack is adjusted to change these values. That's
Thank you guys.
that's all. Thank you so much.